Alright guys, welcome back to the physics lecture series. We're on unit 1 on video 3 and we are starting to accelerate into this, and I just made a pun and it's bad. But this lecture series is presented by Spencer Sabatino and Will Cotter. It's a pun because we're going over acceleration today, constant acceleration, how to show constant acceleration with a particle diagram, and free fall featuring Mr. Tom Petty. So we're going to get into this and kind of talk about everything. So let's start with what acceleration is. So I wanted to start out with this because I think that if we're new to physics, we have so many old ideas of what we consider acceleration to be. And what you probably think about when you think about acceleration is a car that's accelerating forward. Well, I'm here to tell you that your idea of acceleration is different from physics. And I'll explain to you how that is. But in order to first understand that, we have to explain the idea of what acceleration is, of velocity. Velocity is directional. We already talked about that, right? Velocity is directional. Velocity is both speed and direction. It is the rate at which distance moves. The rate at which displacement moves. And that's how we're able to figure out, how fast somebody is going and what direction are they going. And with that being said, we can ask ourselves then, what if we want to take a rate of how our velocity is changing with respect to time? Well, that's exactly what acceleration is. Acceleration is how our velocity is changing with respect to time. In other words, dv dt is A. And so hopefully that makes sense when I explain that. dv dt is A, and and that would be on a differential level, but on a more interval level would be delta v over delta t. So if we were to find an average acceleration over a time interval, then we would have we'd have the starting, so we'd have an initial velocity, we'd have a final velocity, and then we'd take vf minus v aught over tf minus t aught. Pretty simple. So you can think of velocity to acceleration as displacement to velocity, if that makes sense. So in other words, if we take a derivative with respect to time of displacement position s, if we take that would be d dt of that, which gives us v. Well, if we're to take the derivative with respect to time of v, then that gives us dv dt, which is a, acceleration. And that, my friends, is what acceleration is. With that being said, you might be like, at this point, you might be saying, oh, that's exactly what I meant with the car. Well, not quite. Here's why. Because when a car is moving forward, the idea of direction, you can never go a negative speed. In other words, you can't take back 5 steps. However, you can take 5 steps back. So the idea is we can have an arbitrary direction. I mean, your back might be my forward, and vice versa. So the idea is when we talk about negatives, yes, they can cancel out, but it's a difference between displacement and distance. So let me explain it this way. And this is important because it comes into acceleration, but let's say we have a person here, and let's say they're running suicides, if you've ever ran those in a gym. Well, you run and then you touch a line and then you run back to where you were. Well, the idea is, as you know, you certainly have ran because you're probably pretty tired after them, but you're at the same point that you started. So your displacement is 0 meters. But let's say, I don't know, you're here 15 meters. Let's say it's 15 meters. That means your distance that you ran was 30 meters. And that's why when we talk about displacement versus distance, they're different. So this would be distance and total distance. They are very, very different. And so when we talk about displacement, displacement is to velocity as distance is to speed. So we have to understand that, because we have to understand that a velocity keeps direction intact, but we can't have a negative distance and we can't have a negative speed. Total distance is what I should say. Total distance, just for all clarity. We can't, in other words, we can't be taking back steps, but we can take a step back, if that makes sense. Once we take a step, we can never take that step back. We can never have not taken that step, if that makes sense. However, our displacement, our position can be made the same by taking a step in the opposite direction. So if we step forward, then we can step back and be in the same position. Having said all of that, hopefully now that's starting to make a little bit of sense. But if we, let's bring in the car. Well, when you're talking about accelerating, you're talking about accelerating in a particular direction. Well, as we already discussed, for the most part, directions are arbitrary. So we can define one direction as positive and one as negative. So let's define this way as positive. And normally, as we're moving to the right, that's considered positive. I mean, we write left to right, and then, more words as you write left to right on graphs. We consider as we go more right, it's more positive. But we could very easily consider this a negative. So we consider this being more negative as we go forward. So, however, let's just do positive for right now. Well, the idea is, if you're quote unquote accelerating like a car, your velocity is positive and your acceleration is positive. In other words, your acceleration is moving with your velocity. So, as the car is moving, it's starting to move more and more and more and more and more and more. So, the idea there is that you are speeding up. In this case, if your acceleration was negative, the acceleration would be moving toward this way, and so then your velocity would decrease, and you'd be, let's say this is your velocity. And that's a vector hat, but we'll go over that actually in this video. But you would be slowing down. You'd be slowing down if your velocity if your acceleration was negative. So in order for you to be speeding up, your signs have to be the same. Remember, the sign is arbitrary. In this case that we chose, it was positive. The right side was positive. We could have made that negative, and therefore if both signs are negative, it doesn't mean that we're slowing down. It just means that we're speeding up in a different direction, or on an arbitrarily chosen direction. So what's important to pick out about acceleration is that it is the rate of change of velocity with respect to time. All right. Let's go on. Let's talk about constant acceleration kinematic equations. So, now that we've discussed that acceleration is in fact the instantaneously is the differential of dv dt, and we said on a scale that's delta v over delta t. Well, now what we can talk about is that means that vf minus v naught over delta t is going to be equal to a. So let's simplify that a little bit. and then we can say multiply this delta t, and remember this is just a time interval, so we can do this, and we can say that Vf minus V aught equals at delta t, and then we can say that Vf equals V aught plus at delta t, and that's going to be our first kinematic equation that's going to be used so much as we go on. And so I would heavily consider that with these equations I show today, you remember them. However, you should be able to derive them if you ever were on exam and you weren't able to quite remember something, or maybe you're doubting yourself. Well, you could be able to derive them. However, you should be able to remember these because these are the basis of constant acceleration kinematics. With that being said, let's talk about a little bit more. Now we want to derive equation 2 from equation 1. So the idea here is that Vf is ever changing, and Vf is what we're after when we're talking about 1. V aught is a constant, really. It's a constant because it's what we started at. It's the the velocity we started at. It's synonymous to the idea of position and displacement. And so with that being said, if we were to take an integral of this equation, and let's consider delta t to be a variable, almost like x would be in calculus, delta t, well actually let's do this. Let's say delta t equals x. In this case, we would say Vf equals V aught plus at times x. Well, remember, this is a constant, and this is a variable. Vf, final velocity, is a variable. That's what we're after. So what we can say is that if we take the integral, then what we're able to do is, it's power rule. We can figure out that Vf is now going to be SF. It's going to be our position. We know that we need, where we would normally put a constant of integration, C, we can call that S aught, and that's going to be for our initial position. And then remember, the V aught is a constant, so V aught times x, and then in this case we're going to say 1/2 atx squared. And remember that we said delta t equals x. So what we can therefore say is that SF equals S aught plus V aught delta t plus 1/2 at delta t squared. And that, my friends, is equation 2. It is just that simple. It is taking the area, an integral of them, and I didn't really write the integral too well. I guess I could have. But I think you guys got the point to this point. So equation 2, there's where we are. Now we need our third and final equation. And with that being said, we are able actually to use 1 and put it into 2. We already discussed that AT equals Vf minus V aught over delta t, and so let's use this. And now let's just plug that in let's now rearrange them. Let's rearrange this equation, and what we're going to say, we can say that delta t is equal to Vf minus V aught over At. In this case, we're going to use this equation, and we are going to plug it into equation 2, this new manipulated equation. We're going to plug it into equation 2 for all the delta t's. We can say SF equals S aught plus V aught times Vf minus V aught over At, and then plus, I'm going to try to give myself some more room. Plus 1/2 At Vf minus V aught over At squared. Well, once we go through the algebra of all that, what we're actually going to end up with is this final equation. Vf squared equals V aught squared plus 2a delta s, where we could say Vf squared equals V aught squared plus 2a sf minus s aught. So, alright, so that's going to be our third, actually let's use the one on top. This is going to be our third and final kinematic equation. Hopefully those all make sense with the ones that I've explained. So I would say memorize this, Vf equals V aught plus A delta T. Memorize this, Sf equals S aught plus V aught delta T plus 1/2 AT delta T squared. And then finally, memorize this one, Vf squared equals V aught squared plus 2A delta S. And good. So with that being said, remember that we can only use these equations when there's constant acceleration, which means that our velocity is invariably going to be changing because we have constant acceleration. That's acceleration, as we just explained, is the rate at which velocity is changing with respect to time. So if we have a time interval, we know the velocity has to be changing. And that's why we, especially, look at equation 1, that's why we're trying to find the final velocity. By how much does it change? Good. So that being said, we will now go on to our next idea. Now let's model constant acceleration with particle diagrams. Well, particle diagrams, they're actually quite simple. And I think that you guys will find that simple as well. But there is one quick thing we have to hit as we're hitting it, and that's the idea of a vector. A vector, if you guys can't tell from Despicable Me with the superhero villain that says he's fighting crime with direction and magnitude. A vector has to do with a magnitude. A scalar is solely a magnitude, but a vector has both a magnitude and a direction. And so the idea there is that we are dealing with the direction just as we discussed with velocity is both speed and direction. Acceleration is directional. Constant acceleration means that we're moving in the same direction. And that's why when we draw these diagrams, we have to draw in a specific direction, and the vector at which we show it with has to be consistent. So let's draw a particle, and let's say this particle, and this is not the model, but just kind of to explain it. Let's say this particle is moving and it's speeding up. Well, how are we going to show that? I'll answer that. And I'm going to show the diagram here in blue, but we'll start with the particle, and we're going to show, let's say, velocity here. Velocity, we draw an arrow over the V to signify a vector. We will talk more about vectors later, but just as general conceptual ideas, hopefully that makes sense. You guys understand that. But we're going to show, since it's speeding up, we're going to show that the magnitude of the arrows are going to increase, or the length of the arrows are going to increase. That shows that the magnitude of the velocity is increasing. But keep in mind, with each arrow, we're trying to show it that each arrow it's not more time, it's the same amount of time with each arrow, but because we're speeding up, these arrows have to be growing to show that our velocity is increasing over the time interval. Of course, we are moving at a constant acceleration, so we have to be able to show that our acceleration vector is not moving or is not changing length. It is a constant acceleration. It should be, and it's not perfect, but hopefully you guys understand that the all of these top arrows, these acceleration arrows, are supposed to be the same length. And keep in mind, they're the same direction as well, which shows how we're moving in a constant acceleration. It's the same direction. Acceleration is directional. If we were to be moving around in a spiral, not a spiral, but a spiral, well, what would be happening there is we are not moving at a constant acceleration, because remember, acceleration is not a scalar, it is a vector. It is moving with direction. So if we're moving at a constant acceleration, we have to be moving in a straight line. If we're changing direction, we're changing the acceleration at which we are moving. So that being said, hopefully that makes some sense. Let's show slowing down, and hopefully, and keep in mind, as we already discussed, speeding up means that the that velocity is positive and acceleration is positive, or velocity is negative, acceleration is negative. We could deem this as being positive or negative as we go this way. Let's say it's positive. Well, that means the arrows are moving in the same direction. If we're slowing down, then it's the opposite. We're going to see that we're going to start out big just to emphasize slowing down. So start out with arrows being a little bit bigger, and the magnitude of the velocity is going to decrease as the time interval goes on. Remember that between this point and this point, this point, this point, this point, these are all the same amount of small sub time intervals within the overall time interval. And this time, instead of the acceleration vector going this way, it's going to be going the opposite way. It's a constant acceleration, so it's still the same length of arrows, but it's going in the opposite direction to denote that we are slowing down. Almost as if you saw a red light and you were slowing down your vehicle to be able to stop at the red light. You want to hit your brakes. The brakes are trying to, stop the inertia, break the inertia of your car going forward. And so that's exactly what you're doing. Your brakes are applying in this case, if we were to say positive, negative, your brakes would be applying a negative acceleration to combat the positive velocity that you've already gained, if that makes sense. And finally, we are going to talk about free fall with the Tom Petty. Little joke there. If you know, you know. But free fall. Free fall is basically explaining anything, any object, any particle that is just moving down at our place on Earth. That's kind of what I kind of hope to convey by this part of the video. We are moving straight down. We're not moving slanted to the side. That's something we call projectile motion, and we're not projectile motion. We don't want to be talking about that yet, but we will incorporate a lot of the same concepts we learned right here. And free fall is a great example of constant acceleration because, yes, as you go up way, way, way afar from the Earth's gravitational center, you're going to see different values. And, if you were to look toward, very on a micro scale, as you go up 30 feet, you might see a little bit of gravitational difference, but it's negligible. So we can basically say that that gravity is a constant acceleration down. It's our weight. Our weight is force, weight is our mass times gravity. And this gravity is a constant acceleration down. So if we were to let's imagine a ball being dropped from like a 50 feet building, 50-foot building, a ball is just like dropped. Well, if it's dropped straight down and it's not thrown, well, the idea is we would start out with, a little velocity. Let's say you gave it a little bit of toss down. Well, the velocity would be moving down a little bit. So the velocity there, I'll kind of write it like that. But the acceleration is there. The acceleration is certainly there. Acceleration is there, acceleration is not going anywhere, and you're just going to see that it makes sense. As the ball keeps going down, it's going to get faster and faster and faster and faster and faster. And so, like, the idea, I don't know if you guys have ever heard this, but if you're on top of a skyscraper and you were to, like, drop a penny, then the penny can become, like, deadly if it's the skyscraper's big enough, because it's this idea right here. It's this idea. What's ended up happening is that this G, this value of gravitational pull, is making the velocity of that penny so much that the momentum that it has, which we'll go over momentum later, but that's m delta v. The momentum that it has is so much that it could literally go through somebody's head, which is absolutely crazy and super dangerous. But yeah, that's a direct example of free fall of constant acceleration. And so in this case, you can kind of see that, and I should have drawn the ball or object or whatever it is, but hopefully you can see that our arrows for velocity are getting bigger. Acceleration is always down, but the acceleration is the same length and it's not moving. Not greatly drawn, but you get the point. If we were to throw a ball up, well, we know that it would go up, it would stay somewhere, and then it would go back down. And the reason is because on the way up, on the ball's ascension, it's still facing the same acceleration, but in the same direction. But this time the ball is moving in the opposite direction, and the acceleration is moving down. And acceleration is moving down, so we can see that. We can see that the velocity is going to decrease until it's literally going to become zero, and then the opposite, what we explained here, the ball is literally going to start gaining traction as it goes back down. So we go from slowing down to speeding up. And with that, we'll have a lot more examples to go over, but that is free fall. That is the idea of free fall, that there's the only force that is going on us. Of course, we're always going to have a little bit of drag or wind resistance, but a lot of times it will be negligible. But for the most part, the only force that's going on is our gravitational force. And so with that being said, as we're going through different problems, our gravitational force is 9.81 meters per second squared, and I believe it is 36 point, sorry, not 36. It's 32, and I'm looking up the correct number right now. But 9.81 certainly, and then 32. It looks, yeah, you guys would just be fine with 9. So yeah, you guys should just be 9.81 meters per second squared. As long as you know that, you should be good to go. But remember that this gravitational pull is always going down. It's never going up, so never make that mistake. And with that being said, a lot of times, with these questions in physics, you're going to draw diagrams. Like, think about what's happening. If you get something that you're like, this doesn't make sense, then ask yourself, why doesn't it make sense? And a lot of times, as an engineer, as a scientist, as somebody in a STEM field, you're going to be able to understand that you can use the reality test. Like, does this make sense? Even though I was able to get it out of an equation, does the physical result make sense? Like, can I see this actually happening? That's a great lesson beyond physics. But with that being said, hopefully you guys enjoyed the video. I know that I went off on some tangents here and there, but I really do think that everything is going to come back full circle. So I hope that you guys did enjoy that. And with that being said, all of this stuff is just basics. We're going to continue to build on this. And I hope to see you back for the next video. With that being said, feel free to reach out, leave a comment, and I will be sure to answer any questions that you guys have. And with that being said, thank you very much for your guys' continued patience with this series, and I hope you guys have a great night, great day. Also, don't forget to leave a like and subscribe.